Hello, JCDL audience. I'm going to present to you our paper titled Supporting the Exploration of Semantic Features in Academic Literature Using Graph-Based Visualizations. This is what I'm going to cover. First, we'll look at the problem I'm helping to solve with this research, which is that literature search and recommendation systems do not support the discovery and examination of certain semantic features that exist in academic literature, but which are of interest to researchers. And I will introduce those features to you soon. And then second, I'll introduce the RecVis prototype, its system architecture, and the novel interface design that we propose to address the existing shortcomings. And finally, I will briefly discuss the user study we performed, the results, and our plan for future work. So this comic here nicely summarizes the amount of frustration that users experience when they can't find what they're looking for, which is almost unimaginable nowadays. And if Google doesn't return any results, we think we broke Google. So we're quite spoiled nowadays in always getting our information needs answered, but it actually still happens that there are no results for certain information needs. And I'm going to give you examples of that in my talk. So this brings us to the research problem in the context of academic literature search, and the analysis of textual similarity in search and recommender systems is, of course, the most widespread approach, especially for content-based recommendation systems. But we know that academic literature contains not only text-based similarity, so matching keywords or semantically related concepts, but also a range of other non-textual features, as we can see here. So here we have examples of citation pattern similarity, which are obviously present in academic literature. And the more citations match among publications, the higher the similarity or relevance of those publications. The same holds true for figures, charts, images, and of course also mathematical expressions or formulas. So these are features contained in real academic publications, which I have as examples here. And so we can see that the scientific literature contains a range of semantically rich features that really go beyond textual similarity alone. But these features are currently not being considered in existing literature search or recommendation systems, although there's a range of similarity measures that can be used to detect these features, but they haven't been applied to the use case of literature recommendation systems yet. So this brings us to the shortcomings of existing research paper recommendation systems. And I'm just going to summarize two shortcomings. The first would be an inefficient user exploration of the recommended literature. This is the case for the features I just presented to you, because these kinds of features are buried within the text and they're very hard for the user to find by looking only at a recommendation list such as this. So if you imagine any digital library, whether ACM or PubMed, or in this case, the Google Scholar recommendations, you're always presented with a list-based view with some arbitrary cutoff value, and the papers are ranked according to the relevance. But if you're looking for a specific feature, this is not the best way to be able to find those features. So the discovery of these text-independent similarities is not supported. And furthermore, existing research paper recommendation approaches, they lack a lot of user control and have a low transparency, which is of course a general problem facing today's recommendation systems. But in the case of literature recommendation, this is a problem because users cannot control the thresholds for specific types of features that might be of interest to them. And now, before I show you a demo of our RecVis interface, I will briefly summarize the system architecture, because RecVis is implemented as a 3-tier web application, and the front-end presentation tier provides the recommendation visualization interface that we describe in our paper, but the RecVis also connects with the HiPlug backend. So the backend of HiPlug, of course, HiPlug was developed by our group as well, and the backend uses the PubMed open access subset with around 180,000 biomedical articles, and also just over 100,000 archive publications from the dataset of the NTCIR-11 math information retrieval task. And we use these datasets because biomedical publications and math-heavy disciplines, of course, contain more specific features that RecVis is designed to support. So figures, charts, diagrams, citations, and the mathematical formulas. So very briefly, I just wanted to show you the similarity assessment approaches that have been implemented in RecVis. And since RecVis makes use of the high-plug backend, this is only a review of the publications that our group has already published in the past. So I'm not going to, I can't cover these measures in detail because of time constraints, but I wanted to cite these two publications where we introduced various figure-based similarity assessment measures and mathematical-based similarity assessment approaches. And now it's time for a demo. Here we see the recommendation exploration view in the form of a force-directed graph layout, and the recommendations are arranged as nodes around a selected publication at the center. Recommendations with higher similarity scores are shown in bolder colors and thicker connecting lines for quicker identification. And second, we see the feature filtering and comparison view, which lets users quickly filter the recommended documents according to the features of interest. To evaluate the front end of our RecVis interface, we designed a user study with 12 STEM researchers at the PhD and postdoc level, and we aim to answer the following research questions, which were whether graph-based visualizations allow for an efficient exploration of the recommended literature, and if user-controllable similarity thresholds were intuitive to support the discovery of the different feature-based instances of similarity. And to be able to assess this, we made use of the standardized NASA task load index, which is a questionnaire to measure user perceived cognitive workload. And then we also designed a survey tailored specifically to our system where we assessed user satisfaction regarding certain design choices on a 5-point Likert scale. The results of this initial user study were very promising. So first I wanted to say something about the demographics. The average age was 29 and 75% of our participants were very familiar with academic literature search or recommendation systems. And this interface we propose is of course one that will especially benefit expert users, so researchers that regularly search in the literature for very specific, to answer very specific information needs. And regarding the tasks that we gave the users, we had 6 tasks that were related to the exploration view and 4 tasks to be performed within the comparison view, and on average over all tasks and all users, the task completion rate was 93%. And we were very satisfied with this performance because given that our proposed interface actually allows participants to find answers for information retrieval tasks that cannot be answered using any existing exploration interfaces for academic literature, we found that this completion rate was very positive, and definitely the NASA task load index also showed similar results. So the users said that they perceived the success of accomplishing the tasks, they thought it was very high, and the effort or frustration level they rated as very low on average. So these were promising initial results, and of course the questionnaire that we also gave users at the end of the study to gather responses for future improvements really helped us gain ideas for the next and the planned detailed comparison view. So now that we have this new visualization concept, the next stage in our research is to propose a more detailed comparison view where the users will be able to compare the features side by side and be able to discover things that they otherwise wouldn't have found in the literature. And if you have any questions, you can get in touch with me. And here we have the links to our code and data on GitHub. and the link to projects and publications by the Data and Knowledge Engineering Group at the University of Wuppertal as well. So thank you. Bye.